Good morning, everyone. We are Team 5, and today we are excited to present our semester project, the KARD programming language. The name KARD isn't just random, it represents our team. Myself, Kunj, along with me, Aditya, Raj, and Deep. Building a programming language is often considered the ultimate test of a computer scientist's understanding of how computers actually think. Our goal wasn't just to make something that works, but to build a complete, transparent pipeline from raw text to execution. Let's dive into how we did it. So, what exactly is KARD? At its core, KARD is a lightweight interpreted language built using Python. We chose a clean C style syntax because it is familiar to most developers, which lowers the learning curve. Our primary aim was to implement the big four steps of language processing from scratch: the lexer to read the text, the parser to understand the structure, the AST or the abstract syntax tree to represent the logic, and the interpreter to actually run the code. For our tool set, we made specific strategies choices. Antler 4 was used to generate the lexer and parser because it handles complex grammars efficiently. We chose Python for runtime and AST construction because it's flexible with data structure. To ensure our build structure is professional and reproducible, we used CMake. And for version control across the team, we used GitHub. Language feature and architectures is the key part of our next slide. We didn't want KARD to be a toy language that can only add numbers. We wanted it to be functionally robust. We implemented core types such as integers and booleans, but also string handling, which adds significant complexity. Arithmetic to support all standard operations, including complex chained equation like 3 plus 5 minus 9 plus 4. Logic. We have and, or, and not operators, along with fully relational operations like greater than or equal or not equal. Control flow. This is the hard part. We implemented if, then, else blocks and loops for loop and while loop. Special features include ternary operator, which allows concise conditional logic. This was a stretch for us. Now, I would like Aditya to take over from the next slide.
Hello everyone, my name is Aditya Thakur and I'll be explaining you the architecture diagram, the lexical analysis and the parser rule and the CFG. So let's start with the architecture diagram. So this is the heartbeat of our program and how it works. So you can see there is a source code that is entering the system. It passes through a lexer, which breaks it down to the tokens, and this parser organizes these tokens into a tree. And the Python interpreter walks that tree to execute the logic. Having this separation of the concerns made this debugging easier since we knew if token was wrong or if it was the lexer or if it was the logic or the interpreter. Let's move on to the lexical analysis after this. So looking at this lexical analysis, the first steps for it is to have 25 distinct token types in KARD.g4 grammar file. And the lexer's job is to throw away these things that don't really matter, like white spaces and comments, and keep what does, like identifiers, keywords, and literals. You can see here that the sample factorial.card uh, tokens, um, the raw code is chopped up into digestible pieces for the computer. Let's move on to the next slide for the parser rules. And once we have all these tokens, we just need a grammar. And for that, we have designed a 100% LL star grammar. Next slide, please. For those less familiar with compiler theory, that is essentially that means our grammar is efficient and free of ambiguity. There are no conflicts, and there is a part if the parser gets confused about which rules to apply, We also eliminate left recursion, which is a common pitfall that can cause parsers to enter infinite loops. This grammar generates a clean parse tree, which can then be converted into our own abstract syntax tree. And now my colleague and friend Raj would take over and explain what's the abstract syntax tree.
Hi, this is Raj, and I'll be explaining the expression hierarchy in our project. So, one of the biggest challenges in language design is order of operations. If there's an expression, say 2 plus 3 into 4, the answer should be 14 and not 20. This slide shows how our expression hierarchy. We structured our grammar rules to inherently respect precedence. Multiplication and division sit higher in the tree than addition and subtraction, ensuring that they are evaluated first naturally without us needing to write complex custom logic to handle it. So, given this table shows the expression hierarchy in the order. Next is abstract syntax tree or AST. The parser gives us a raw tree, but the AST is where the magic happens. We created a Python class called AST node. So the UML diagram shows the AST node, and this serves as a blueprint. Every meaningful construct in our language has a corresponding node type. Binary nodes for math, if and while nodes for control flow, print and var nodes for input, output, and memory. This simplifies execution. The interpreter just visits the nodes and recognizes what that node is. If it's an if statement, then it has to check the condition, if the condition followed by the if statement.
Hi, so myself Deep, and I'll be showing how the ternary operator works on our upper code. So right now we have a condition that is 10 is greater than 5. If this is true, so the question marks, the next value of after the question marks works as a yes, and and as a true value that this is a boolean as a true, and we consider the first value as our uh, right value, and then if it's wrong then we'll go for no. And this is how it works as a ternary operator in our code. It also works like same. Then we have validate our language in such a way that there's three major key programs we have validated. First of all is arithmetic card and nested block card. So here it is the uh, picture of it, and I can show the how the process is working. So I have tested many times about how we are doing it. So we have a main file where we are doing the implementation or running the code. So we need this file. I'll show in another terminal so it will be more good to understand. So we'll write Python KARD.py, then the address of the like the relative path of this thing, and then just paste it. Right now I'm doing this complex program.card as an example. If it's working, then if it's x equals to greater than is greater than 5, then we are doing y equals to x plus 1 and all stuff. Then we have arithmetic dot card 1 plus 2 plus 3 plus 4. We are just running this. Uh, I think I have this. Here you go. So the sum of this is 10. 1 plus 2, 3, 6, 10. So yeah, it's giving the correct answer. And if you want to run the bat file, we have all the test cases running, like 13 test cases, 1 to 13. All the test cases has been passed. And that's about it. And we will talk about the limitations part. So I would say no software is ever truly finished. In the spirit of transparency, we have identified some limitations. We currently lack user definition functions and type checking. Scope nesting is currently limited. However, the functions is solid. Future work, we have a roadmap includes adding repls like read, eval, print loop for live coding, a static checker to cache error before runtime, and model support so file can talk to each other. And that's it about our project. Thank you. Thank you